Thank you for joining the third GEO-Google Programme virtual meetup focused on water quality. I'm Sam Atkinson, the General Manager of EO Data Science, and I'll be your host. EO Data Science is an Australian company specialising in operationalising Earth observations. We're fortunate to have an excellent working relationship with the Google Earth Engine team, and we're even more fortunate to be providing support to the GEO-Google Programme. Our vision for these meetups is for projects focused on similar or overlapping themes to share knowledge, ask questions of each other, and to build professional networks. Travel and conferences are, of course, nearly impossible due to COVID, but we want to enable as much sharing of ideas as possible. With this objective in mind, the structure of this meetup is like a panel discussion. Each of our projects will present for 5 minutes, followed by questions and answers. Then we will take the opportunity to ask as many questions of the panelists as time permits. To ask a question, please use the comments box. And please do ask questions. Please do ask questions and ask them at any time. We'll get to them, we'll present them at the end to the panels. It's really important that we are hearing the questions of participants in the program, because they'll just be far more interesting than my questions and far more relevant to you. So I implore you to please ask questions. The GEO-Google Programme has an amazing global reach with projects on every continent. In these meetups, we're celebrating the diversity of objectives, methods, perspectives, and people that you can only really get with a global conversation. So as we engage in this discussion, it is this diversity that offers us the greatest opportunity to learn and share knowledge, in my opinion at least. To enable networking from these events, please look at the speaker and attendee bios that you would have received a link to in the invite to this meetup. If you haven't created your own bio and want to, you still can. If there is a bio you see and you want to talk to that person, please reach out to them. In this meetup, our presenters and panelists are Steve Greb from the University of Wisconsin-Madison, presenting on AquaWatch, Joji Ishizaka from Nagoya University, presenting on near real-time monitoring system for marine coastal eutrophication. Dimos Traganos from the German Aerospace Center, presenting on coastal ecosystems. Nick Metherall from the South Pacific community, presenting on analysis-ready data for water security. Felipe Lobo from the Federal University of Pelotas, presenting on an alert system for algal bloom detection in inland waters of Latin America. We're also hoping to have with us David Fernando Morales Giraldo from the Marine and Coastal Research Institute in Colombia, presenting on coastal erosion and mangrove ecosystems. Finally, we're very pleased to have with us Doug Cripe, who is the Senior Scientific Advisor at GEO, and Noel Gorelick, who is a Senior Engineer at Google and also an Earth Engine co-founder. Noel, would you like to say some words from Google's perspective?
Sure. Thanks, Sam. As he said, my name is Noel Gorelick. I'm one of the co-founders of Google Earth Engine. We here at Google are happy to be able to provide the technical infrastructure for these projects. I'm just here as an observer to see if there are common issues or opportunities to improve the back end to try to help unblock any of the projects that might be having scaling problems using the platform. With that said, I'm anxious to learn more about your projects. Thanks.
Thanks, Noel. Now let's hear from GEO and Doug Cripe.
Okay, thanks, Sam. Hello, everyone. This is I'm very pleased to be here and learn about your projects. The GEO part of this program, the GEO Google Earth Engine program, is what I want to talk about briefly. Some of you may not be aware of what GEO is. So GEO, the Group on Earth Observations, is a global partnership of governments and organizations that envisage a future where decisions and actions for the benefit of humankind are informed by coordinated, comprehensive, and sustained Earth observations. So it's been in existence since 2005, and we have over 100 different governments that participate in GEO in a non-binding best efforts way. If we go to the next slide. The mission for GEO is to connect the demand for sound and timely environmental information with the supply of data and information about the Earth that is collected through observing systems and made available by the GEO community. And in so doing, GEO works to unlock the power of Earth observations by facilitating their accessibility and application to global decision-making within and across many different domains. So we are interested within the GEO community of opening up access to all types of Earth observations, not just satellite, not just remotely sensed, but also in situ and marine and so forth. So I'm looking forward to seeing what you're doing in your projects with Earth observations. And back to you, Sam.
Thanks, Doug. Glad to have you here with us. Now on to the presentations. First, we have Steve Greb from the University of Wisconsin-Madison presenting on the very large project and long-running GEO project, AquaWatch. Over to you, Steve.
Thank you, Sam, and thank all of you for coming today and attending these seminars and talks. I want to take this opportunity to tell you a little bit about our project, and I'm also here to learn about the other projects and you know who's doing what, because I think again we can learn from each other, and I think a lot of us maybe are facing some of the same hurdles as we move forward. So the title of this project is Development of Global Water Quality, Geospatial Products and Tools. Next slide. For those of you who don't know about GEO AquaWatch, GEO AquaWatch aims to develop and build the global capacity and utility of using Earth observations for water quality data, products, and information, and we're here to support water resources management and also the decision makers. AquaWatch has 5 components illustrated here by these 5 circles. The 2 areas that we're going to focus on in this particular project are the observation and data, and of course products and information. All this feeds into what we call the Water Quality Information Service, which ultimately is what we were striving for. And I think this Google Earth Engine project will help advance this considerably. Next slide. So if we look at our project, here are the objectives. 1, provide a global scale, open access, freely accessible, fit for purpose. There's a lot of descriptors here. Water quality information. The parameters that we're going to focus on are chlorophyll A, total suspended solids, and color dissolved organic matter, or CDOM. The geographic domain, the areas that we're focused on are the inland waters and the coastal waters, the nearshore coastal waters. Our end users, it's a wide field from the science community to water resources managers, industry, and the general public. This is a collaborative effort, and we've invested a lot of time kind of bringing some of our partners together in building this group, but it consists of a number of folks from the GEO AquaWatch community, the World Bank, Conservation International, of course Google Earth Engine, and UNESCO. And of course, they all bring their different strengths to this effort, and I think together this is going to provide for a strong effort and activity. Next slide. This is just to give you a sense for who are the players in this effort, or our study team. A lot of the folks that are listed here are part of the algorithm focus group, which I'll talk about in a minute. But you can see there are folks that come from a number of different agencies and academic institutions from around the globe. Next slide. So this was in the proposal, the general project workflow that we started with, essentially going left to right. Starting with this algorithm focus group. This group was going to develop an algorithm strategy, if you will, on which are the best algorithms to use for what particular types of water. And then these recommendations would go to a group, either some of the algorithm folks themselves or the World Bank to help write the scripts and APIs. And then that goes to a product testing. We think validation is really an important, critical part of this whole process. And so we are really putting a lot of our products. Next slide. Early on, though, we've learned that that linear model really doesn't follow for what we want to do here, and we need kind of a circular model. So there's feedback and interaction between these three boxes. And furthermore, next slide, what became really obvious early on is that we needed a reference database. This is a big investment, but we needed a standardized database for the different water types from around the globe, be it coastal or inland waters, that these algorithms would be tested against. And this is really important that we do this up front, that we provide this investment so we have this database for the algorithms to be tested against, and so everybody is using the same database, so we can compare metrics and our statistics as we put forth these algorithms. Next slide. So just under current activities, what we're working on now, again, this reference database is really important. We're going to use using the framework developed through the Global Lakes project. It's called Limnades is the database. This is housed at the University of Stirling in Scotland, and so they've actually stepped up and said yes, they'll be the keeper or curator of this database. We also, since then, although it hasn't been made, it's not official yet, it looks like we probably will get some support dollars through the World Bank to pay somebody to work on this and to help us get this up to speed quickly, because we don't have a whole lot of time. I mean, this project, I guess we're already 6 months into it. The second major point here is, again, developing an algorithm strategy. As you know, there's many different types of algorithms, which is the best and what works best within the framework of Google Earth Engine. So we've just sent out what's called a survey to the algorithm experts, where we're asking them to nominate algorithms, be it an algorithm for a specific application, eutrophic inland water of a certain size, or whether it be something more universally applied. So we're right now in the process of receiving those nominations back, and that ends this Friday. At that point, we'll summarize the nominations we have, and we'll call a meeting of the algorithm experts, which there's 20 of them on this team, and we'll decide a way forward. The third thing is, of course, a number of our team members are taking the Google Earth Engine classes that have been offered. Next slide. So I'll quit there. As far as contact information, for those of you kind of interested in this project, please reach out to me directly at the University of Wisconsin here, either my GEO AquaWatch email listed there, or my University of Wisconsin email. And feel free to visit our website, geoaquawatch.org. We're always interested in having more people. For the most part, AquaWatch is a best effort, which means it's a volunteer, it's nights and weekends, and so we appreciate all the help we can get. So Sam, I'll turn it back over to you there. Thank you.
Steve, thanks. Yeah, I definitely encourage anybody who isn't familiar with AquaWatch to check out the website. There's a lot of really relevant information in there if water quality monitoring is your particular area of interest. Steve, I wanted to ask you, and again, just because we haven't got any questions from the attendees, so I'll ask one of my kind of selfish questions. How sensitive in general are water quality algorithms to small water bodies? So kind of in my part of the world, in particular, where I've worked a lot in semi-arid areas, the water bodies that are, really ecologically significant can be quite small, a few to several, sentinel-2 pixels wide. Is that kind of a current consideration of AquaWatch research on those smaller water bodies, or, what's your experience in that?
Right. So, water body size is an issue, and it's as much the shape of the water body as it is the size of the water body. I mean, you can have, a round or a square water body that would be more efficient in terms of getting pixels in there. We try to find water bodies, or find 3x3 matrix of pixels that to average, as a minimum. So with the resolution of the satellites, and like the Sentinel-2 and the Landsat-8 at 30 meters, that kind of limits you. There's also issues with like adjacency effects, depending on what's around that water body can have some interferences. So that's another consideration that we're looking at. But you're right, there are a lot of small water bodies. We just had looking at some ponds, which actually play an important role and are important in terms of movement of nutrients off the landscape, but they can be hard from satellite remote sensing.
Yeah. Okay. Great. One other quick question. The database of reference data that you guys are putting together, are there plans for that to be kind of open to the public or other researchers to access?
Most definitely, and that was a prerequisite for building this database. This was going to be all open and freely accessible. And I see the question here is, will it include IOPs or the optical properties of the water, the inherent optical properties, and yes, it will. That's one of the things needed, of course. We've talked about it at great length, and so I think there'll be a set of IOPs and related water quality parameters, and then there'll just be some water quality parameters, which we have a lot more of, just plain water quality data. And I see Doug has a note in here too about any of the algorithms you're considering AI. So there has been one AI approach that's been proposed so far, but I think that's definitely an area which we're seeing more and more this field headed towards.
Fantastic. And one last question. If somebody's listening to this and they have water quality data, and I think that'd be great to contribute to the database, would you be the best point of contact, or AquaWatch in general?
Yes, either one, but if you could contact me, that would be great. And I think, maybe when we get into the discussion further down in the program today, again, I would encourage the other folks or team leaders here that maybe that might be one point of collaboration. So yes, it's definitely going to be public and freely available. That was requisite of the group.
Excellent. Steve, thank you. We look forward to continuing this discussion with the other panelists in about an hour's time.
Thank you.
Our next presenter is Joji Ishizaka from Nagoya University, presenting on a near real-time monitoring system for marine coastal eutrophication. Over to you, Joji.
Okay, thank you. Thank you for giving me the good chance for presentation here. So my name is Joji Ishizaka. I'm from Nagoya University, Japan. The Institute of Space Earth Environmental Study and Research. And so our project, development of near real-time monitoring system for marine coastal eutrophication using Google Earth Engine. So the Steve mentioned that for his project that they mostly focusing on, I guess, algorithms issues. And actually our project is try to use just the present the products mostly of the ocean color satellite, the chlorophyll A, which is known as a kind of indicator of the eutrophication. Can you go to the next? Okay, so here, yeah, the eutrophication is kind of yeah, probably everybody knows that yeah, the mostly human activities in the accelerated eutrophication in the mostly coastal area. We are putting nutrients into the coastal waters. So the response, one of the well-known response of this eutrophication is the increase of the phytoplankton, so which often makes too much organic matter, and so often makes the anoxic condition in the bottom, and or sometimes there's some harmful algal blooms issues. So it is yeah, necessary and that to understand whether the region is eutrophicated or not, or it is increasing the eutrophication condition or not. Yeah, I guess in right now the most of the world coastal area, there's many area that which is influenced by the eutrophication. And actually, but in some area, it is interesting. In like in Japan, there's some discussion about opposite direction, the so-called oligotrophication. That yeah, because we have a long history of the eutrophication, and then the government tried to restrict the input of the nutrient into some areas, and that seems like reducing the primary production, and some fishery people claim that it is influence to the fisheries. Yeah, so of course it is not still very clear about this issue, because this is a more recent issue. But I think it is very important to understand which area is eutrophicated, or eutrophication is proceeding or not, or decreasing, like oligotrophication. Yeah. So yeah, can go to the next. Yeah. So our goal is objective is to develop a rapid global scale preliminary assessment tool of potential eutrophication areas based on the Google Earth Engine and satellite chlorophyll A. So as Steve mentioned, actually the algorithm issue is very important for coastal area. Yeah, so sometimes the chlorophyll may or may not be true, but it is important to understand the condition, at least that possibility. Okay, so we are trying to make a kind of warning system for the eutrophication, so that policymaker can work quickly, that whether they have to check the coastal area is really eutrophicated or not. Okay, so this is so in this sense, it is kind of, yeah, the even chlorophyll is not very accurate, that I think it is useful. So we are thinking that use mostly present product of the satellite, but of course, if we can develop, or the Steve's project to develop a new good algorithm, maybe we can import that kind of algorithm. So this figure shows the way that we are trying to do is, so we already have more than 20 years of the ocean color, the database. Yeah, it's a long history of ocean color. So we can see there's a region of the high chlorophyll or low chlorophyll. So the above one is high and the bottom one is low. Okay. But also, we also know, because we have a long history, we can check whether the chlorophyll is increasing or no trend, or decreasing. Okay, so if we have the increasing trend, maybe it is becoming eutrophicated, or decreasing, maybe becoming oligotrophicated. Or, yeah, of course, we can so we can have two different view that the present condition and also the trend of the chlorophyll. Okay, so that those 6 categories should be very useful for the policymakers to decide whether we have to do something. Okay, next slide. Yeah, so actually we are already working on our area. I'm from Japan, and we have one of the UNEP project, regional sea project, so-called NAOPAP, which is Northwest Pacific Action Plan. So we are trying to see in this region whether there are some region is eutrophicated or not, okay, or the eutrophication is increasing or not. Yeah, so as you may know that this area is very the human populated region. Because it is Japan and Korea and China, and also the Russia is part of this area. So we know the human activity is very high, and some region is definitely eutrophicated now. So we are trying to make this system to so-called as you can see on the right hand side, we can see the chlorophyll concentration and the trend, and makes those 6 different trend condition. Okay, so we are already working on this, and then we are trying to do more. Can you go to the next slide? Yeah, so presently we only use some the satellite so-called seaweeds and MODIS, which is very popular with 1 kilometer resolution. But since we want to see a more coastal area, we like to include more higher resolution satellite like SGLI from Japan, and which is 250 meter resolution, or Sentinel-3, which is 300 meter resolution. And of course, we also need to include more recent satellite like VIRS. So we try to put those data in the Google Earth Engine, so that we can see the global view very clearly, or even the regionally to analyze. Okay, can go to next. Yes, so this is one example that we are trying to do for the global perspective view. And as you can see, it's kind of interesting if you look at the very large scale like this. Some of the open ocean is a decreasing trend, which may be related to the global warming, or possible related to the global warming. Of course, there are some more short-term variation is also available present. So in any case, that we try to do this kind of analysis with the Google Earth Engine, so which should be make a public to help for policymakers. Okay, thank you very much. Yeah.
Joji, thank you. I took the opportunity to have a look at your Earth Engine app. It's a great example of how easily you can communicate what is reasonably complicated science to users with a simple URL. I'll try and post that in the comments for other people to click on and have a look. I'd encourage them to have a look. It's a really good example of an Earth Engine application to inspect any part of the ocean in the world that you are interested in. So thank you for that. I did have a question. How variable do you find satellite-derived measures of chlorophyll A? And is that variability related to kind of real short-term changes in chlorophyll A, or is there a component of measurement noise?
Yeah, this is well. It is not so easy question to answer, but it is well known in coastal area. There are some problem caused by the sea dome, or which is dissolved organic matter or suspended matter, that which Steve already talked about. It. Yeah, that's why it is really necessary to develop more good algorithms. Yeah, for example, in the Japanese, the Chinese coastal area, we know there is a very, very heavy suspended sediment. So we developed our own regional algorithm in that area, and so that is more helpful to understand. But of course, it's not still perfect. So I'm very glad to hear that the project is developing a new algorithm. So we hoping, yeah. Of course, we are starting to use the more general the available data, but if regionally the new algorithm is available, maybe we can replace those regional bases, or even global bases. Yeah. So open ocean is usually okay, but still there are some discussion. Yeah, because for long-term change, we need to use a different satellite. And then the different satellite have sometimes different calibration and some different sensor characteristics. So there might be some influence, but still, that kind of thing is also you need to clarify with regional data set, as Steve said. Yeah, that so we, at least for our region, that with China and Korea and Japan and Russia, we are trying to work with the regional people, and then to get the verification data, and so checking the algorithm also in that area. So we are, of course, encourage to other regions that this is kind of only I guess the potential eutrophication checking. So the final check should be the regionally really intensive study. Yeah, that is always necessary. But I think it is good to see the potential problem, so that the policymaker can think about the issue. Yeah.
Yeah, excellent. Joji, thank you. Look forward to continuing the conversation later in the panel discussion.
Sure. Okay, thank you very much.
Our next presenter is Dimos Traganos from the German Aerospace Center, presenting on coastal ecosystems. Dimos, over to you. Dimos, you're just on mute. You're muted, I think. Still on mute, Dimos.
Yeah, sorry for that. Thank you, Sam. So good morning, good afternoon, and good evening from Berlin to all participants and attendees in this virtual meetup. I hope you are all well and healthy under the ongoing circumstances. Thank you, Yvonne, Sam, and the entire EO data science team for arranging this great opportunity to share our research and exchange knowledge with all other participants. I'm Dr. Dimos Traganos, and I'm a scientist and project manager for the Coastal Ecosystem Project, working for the last 5 years in the German Aerospace Center here in Berlin, Germany. My team and I are excited for being part of this great initiative by Google and the Group on Earth Observations through our project. I would like to add that the Coastal Ecosystem Project is part of a larger DLR-funded technological innovation project called Global Seagrass Watch Project, which aims to map seagrasses and their seascape neighborhoods at planetary scale using cloud computing, AI, open satellite data, and in situ data. Hopefully, my presentation will be able to synopsize the work that we are doing on the scalability for coastal ecosystems using Google Earth Engine globally. Next slide, please. Thank you. Seagrasses, which is our main targeted coastal ecosystem of interest, is underwater vegetation that is found in all continents but Antarctica, and is covering an area pretty much equivalent to the area of Germany. They provide a plethora of valuable yet overlooked, degraded, and unmapped ecosystem services, which fuels our interest into mapping their extent and value. Among other great services, seagrasses protect over 100 million people from coastal erosion, reducing the waves that are arriving in their coastal proximity. They also support up to 1/5 of global fisheries, providing important protein for the diet of billions of people. Last but not least, they can also sequestrate and store up to 80% of the carbon that oceans absorb annually, which is nearly 1/3 more than the annual carbon emissions of the whole cruise ship industry. Next slide, please. Thank you. The quantification of the seagrass-related carbon stocks could inform in a data-driven fashion the so-called national determined contributions. These are conceptualized contributions under the Paris Agreement for each and every country. Estimating the stocks could especially help developing and data-poor regions to curb their industrial emissions and strengthen their national scale climate change mitigation policy and carbon budgeting agendas. Displayed are the only 10 countries globally that have explicitly identified seagrasses in their NDCs as part of these mitigation and adaptation actions. Quantifying the stocks is one of the large aims of our project in an effort to enforce the aforementioned climate policy agendas. Next slide, please. Thank you. Here you could take a short exemplary glimpse into what our end-to-end cloud-native Earth observation processor could produce within the Google Earth Engine platform. At the top panel, you could see an uncorrected surface reflectance Sentinel-2 composite over the middle of Tanzania in East Africa. We are correcting these composites using the so-called multitemporal analytics, utilizing thousands of satellite images to correct the clouds and other optical interferences, estimate turbidity in yellow, satellite-derived bathymetry in the third panel, the so-called soft probabilities of seagrass presence in the fourth panel, and finally, in the last panel, the hard probability of seagrasses using statistical thresholds, which are based on machine learning frameworks. Next slide, please. Regarding the satellite-derived bathymetry product, since the onset of the spring lockdown, we have designed and developed an end-to-end cloud-based satellite-derived bathymetry processor in Google Earth Engine in collaboration with NASA to fuse optical Copernicus Sentinel-2 data with spaceborne NASA ISAT-2 LiDAR data. And we use those to map water depth from shoreline scale in Crete to small island nation scale in Bermuda. This is a purely spaceborne approach which can yield bathymetry in a time and cost-efficient fashion and with errors up to 10% of the total assessed bathymetry. This aids the development of several blue economy markets, including climate change mitigation, disaster recovery, coastal resilience, coastal erosion, and marine navigation. Next slide, please. Thank you. In another recent mapping effort, which has been nearly 2 years in the making now, we employed our seagrass classification framework, over 270,000 satellite images from Sentinel-2, and over 65,000 Calval points to train and validate our seagrass classification framework and map seagrasses for the first time at the entire basin scale of the Mediterranean with an accuracy of 72% over 22 countries and also 50,000 square kilometers of coastal seabed. This paves the way for scaling up seagrass extent and related carbon stock estimations to basin, continental, and ultimately global scales. Next slide, please. Thanks. These latter scales are powered by the computational efficiency, power, and capacity of Google Earth Engine and strengthened through our participation in the GEO initiative. We aim to scale up our mapping efforts to the continental scale of Africa and Asia within 2021, and we will draw experience, inspiration, and capacity to produce the first global map of seagrasses and their related carbon stocks within 2022 to better inform national and international efforts in an effort to inform respective national determined contributions and thus put a small stone towards empowering effective and data-driven policymaking to reduce the impact of climate change on our planet. Next slide, please. With this, I would like to conclude my presentation and thank my partners in crime in this project, Avi and Benjamin, who are doing a great work in programming our cloud-native processing chain. And I will be happy to take any of your questions regarding our work. Thank you.
Dimos, thank you. Excellent presentation. I've actually got quite a few questions, so I'll try and be quick. How globally applicable do you think the turbidity calculation will be, or others for that same matter? Do these measures, really need local calibration, or can they be generalized?
Yeah, that's a very good question, Sam. I think it's efficient and realistic as long as we can synthesize information from satellites, such as the Sentinel-2. That applies also for our other mapping products, so namely seagrasses, satellite-derived bathymetry, etc. Right now, we are using at a national scale. We are testing the turbidity algorithms using training that are designed on the satellite composite itself, but we are really lacking in having accurate in situ data from turbidity to validate what we are producing. So I think our participation in this discussion and what we will learn from other participants will help us understand and realize better the accuracy of these products.
Yeah, excellent. That's always the great challenge with remote sensing, I find, is finding enough in situ data to calibrate and validate with. So one more question on the classification of seagrasses. What was your approach for the machine learning component? Is it neural networks, or is it more classical machine learning?
Yeah, at the moment we are using classical machine learning. We have tested various approaches using random forests, using support vector machines. For now, we have settled with random forests because we have observed that they are more computationally efficient and they work also well and relatively unbiased with even small sample sets. But for the future, for 2021, we are planning to test and explore the connectivity between Google Earth Engine and TensorFlow in order to understand what kind of gains we can have in terms of accuracy, in terms of efficiency, and also to streamline our whole processing chain.
Yes. Excellent, great. And one last question. This one coming through from Doug. For your work that you're planning in Africa, how far from the coast into the sea will you be assessing seagrass populations, or I suppose more generally, how far from the coast or how deep a water can you effectively measure or classify seagrass?
Yeah, that's a very good question. From our experience working in East Africa in a project in collaboration with WWF Germany, we have mapped coastal habitats, including seagrass and corals, up to 15 meters of depth. And I would say that would be a very important component and input into the processing chain and the seagrass classification, because that would designate the optically shallow, what we call in coastal remote sensing, extent of the water column. So essentially where the optical remote sensing signal could penetrate the water column and reflect on the seabed. Yeah, 15 meters would be the maximum capacity using optical data.
Yes, excellent. Okay, great. Dimos, thanks for your presentation. We look forward to asking some more questions of you soon. Next, we have Nick Metherall from the Pacific community presenting on analysis-ready data for water security. Over to you, Nick. Are Are you just on mute as well, Nick?
That's funny. I was thinking I'm not going to do that as well, but I did. Thanks for that. So my name is Nick Metherall, and I'm coming from a hydrology background and working with the Pacific community. My colleagues Carol, Chan, and Sachin couldn't be here this evening, unfortunately, due to the some meetings and time difference. But so I'll be speaking on behalf of our team. So our original project is at more of a we're kind of more a capacity building focus. So at this stage, we're not quite as advanced in our use of Earth Engine. We're still scoping out within the main areas of our projects. So the two main areas on the left and the right are kind of atoll water security assessments, as well as on the right, more of the ridge to reef environmental monitoring. And so listening to all of your presentations has been really valuable, and we're hoping to learn more from them. Slide, please, Yvonne. So I'm not going to go into reading each of these lines, but in essence, we tried to look at the areas of confluence between the water resource assessments and the environmental monitoring that could be supported by remote sensing. Next slide, please. So in terms of our work at the Pacific Community, so the Pacific Community is the regional science and technology for development organization in mostly working in the South Pacific. And so our project will be largely to do with supporting some of our work on the water assessments. So a lot of the work in the past has been focused on groundwater assessments and learning from, I think, remote sensing applications for rainfall and surface water monitoring as well. Next slide, please, Yvonne. So part of the work has been developing a bit of an atoll inventory, which tries to combine these different data sets for rainfall, surface water, and groundwater to kind of come up with an overall indices for water security for some of these low-lying coral carbonate atolls. Next slide, please, Yvonne. And so this is just a bit of it's basically a geodatabase that we're putting together and looking at how we can support this with more remote sensing data through Earth Engine. Next slide, please. And so some of the examples of areas we've been looking at and reading include some of the bathymetry data sets to support bathymetry assessment, looking at different drought indicators, learning about the different rainfall data sets in the training. And we were considering looking a bit more at GRACE for groundwater. However, the spatial resolution may not allow that, but we'd be very keen to learn from others who might have experience in this area. Next slide, please, Yvonne. So the other side that I spoke about earlier was to do with more of the environmental monitoring. In the Pacific, a lot of projects are coming up for ridge to reef, which is the connection between islands and oceans, and very relevant to a lot of presentations on eutrophication and coastal grasses to come. Next slide, please, Yvonne. I'll speak to that. So this is an example of the geodatabase that we've been developing for ridge to reef data. So a lot of water quality data collected in situ, a lot of invertebrate data and ecological data collected. So a lot of field work is going into this. Next slide, please. And so we're looking at some of the different ways to monitor some of the disturbances to these to watersheds and to marine ecosystems. So in-river gravel extraction, deforestation, settlements, and roads. Next slide, please. And yeah, a lot of that is being fed into some of the standard frameworks that are being used for these ridge to reef programs involve environmental modeling using the INVEST kind of ecosystem services modeling software from, I think that's been developed at Stanford for natural capital ecosystem modeling. Next slide, please. And so, yeah, this just kind of sums up the areas of the water resources assessment and environmental monitoring. And next slide, please. And we just wanted to say thank you from our team and to the committee, and yeah, looking forward to learning more from all of your presentations and plenty of questions to ask afterwards. Thank you.
Nick, thank you. Very interesting project, and I think somewhat different in scope from many of the other projects where we are looking at small water bodies, where in fact you're looking at very small water bodies inside very large water bodies, which I think is a particularly unique challenge. I had a question around, it's not so much of a technical question, but certainly from the Australian perspective, my perspective, the Pacific Island nations seem to be really well known for working together kind of across those national and cultural boundaries and across vast distances, right? These are relatively small islands a long way apart. Can you share any insights from your experience on kind of why they work so well together, and what can we learn about how we kind of work together across national boundaries, because I know many of the projects here tonight do have that multinational focus.
Certainly, yeah, thanks, Sam. Yeah, no, it is a good point you've raised there, and I'm seeing some more questions coming up as well. So to answer that, I mean, a big part of our project is largely to do with capacity building across the Pacific. So ideally, it wouldn't be me presenting tonight, but probably more of, hopefully in the following years, if there are follow-up presentations to this, it'll be some of our colleagues in the Pacific. It is a bit of a tough time difference, actually, but in fact, so the Pacific community, we're working across about 14 different countries, including Kiribati. I saw came up in Dimos' presentation about the seagrasses, and it would be good to connect you with some of our researchers doing work on seagrass, and we're very interested to learn from Steve as well, because we talked about AquaWatch. But in terms of working together, it's a good point. I think, yeah, there is quite a lot of Pacific solidarity in terms of Pacific small island developing states, and I think that part of the work that we're doing as the Pacific community is there are networks that have been built across all of the member countries from this kind of it's a bit of our organization, it's kind of an intergovernmental organization, so it supports work across all of these countries, working directly with the members, and so that kind of supports that. But in terms of the wider social, cultural, and complexities, I probably can't go into that, but I think that we're trying to help build on that and work with the community. Sam, so.
Excellent. So of course, we all know the Pacific Islands are, extremely vulnerable to climate change and sea level rise in particular. So how does this project, I suppose, attempt to help to mitigate or understand those potential impacts of climate change?
No, certainly, absolutely. So definitely in terms of on the water security side, certainly in terms of groundwater vulnerability and climate variability indices, that's very true. And then on the environment side as well, I think particularly relevant to some of the other presentations that have come up on AquaWatch and coastal eutrophication and seagrass, about the monitoring of inputs into coastal ocean acidification, which my current PhD will be looking at as well. So about this watershed inputs into coastal ocean acidification. So that's, yeah, I think that, yeah, it's certainly all connected, Sam.
Excellent. Great. Thanks, Nick. We look forward to asking you some more questions during the panel discussion.
Great, and thank you everyone for your presentations.
Thanks. Our next presenter on the other side of the Pacific and even across the Atlantic is Felipe Lobo from the Federal University of Pelotas, presenting on an alert system for algal bloom detection in inland waters of Latin America. Over to you, Felipe.
Well, hello everyone. Good morning, good night, and good afternoon. I'd like to thank you, Sam and Yvonne from EO, for the support you giving us with courses and all the answer all the questions you need. I'd like to thank you also Neil from Google Engine, and and everyone to have your time to be here and share our experiences. My name is Felipe Lobo. I'm currently a professor at the University of Pelotas in Brazil, south of Brazil. And we are currently working with some Latin American colleagues in order to develop a monitoring system for algae blooms in inland waters of Latin America. Next, please. So during this project, we were able to connect with several researchers around Latin America, from Mexico to Argentina. There are a lot of researchers involved, and I'm very happy for that, so I won't name them all here. Next, please. The initial plan of the project is to create this monitoring system for algae blooms, or a trophic level of the inland waters, using Sentinel-2 level 2 collection, or corrected for atmospheric corrections effects. Initially we were planning to use 6S and create a new collection and upload to the Google engine, but it's a very demanding, completely speaking. So we focus on alternative and using corrected images from Sentinel-2 core. Initially we were planning to use the level 2 collection already available Google engine, but we decided to use a different alternative. You'll see again next slide. But no, sorry, previous slide. Okay. So with this Sentinel collection, we plan to create an alert system for detection algae blooms. And we plan to create a time series with this collection, so we can see trends and areas of hotspots, reservoirs, and some water bodies that facing some eutrophication problems. And also we plan to engage with other stakeholders, both researchers and end users, including companies that can use this information for actually water management and use the information for their actions. So that's a big part. So because of the Sentinel core product shows a little, it's not the best correction for water quality applications. So we're looking for alternatives, initially 6S, but next please. We found on Google Engine there's a script developed by a researcher as well that provide the SEAC method for Sentinel-2 correction. And this slide showed that the atmospheric correction, they estimate the aerosol better than Sentinel core, for example. Next, please. So this is the algorithm developed on Google Engine can use the script to correct the images. Next, please. And once you have the image correct for atmospheric effects, we apply the NDCI, which is similar to NDVI for vegetation, but the NDCI is the chlorophyll index, which relies on the response of the spectral response for chlorophyll-rich waters, with reflection here in the red edge band and absorption in the red band. So we are planning to use NDCI as an index. I think that's a pretty interesting way to do it, instead of trying several algorithms and different adjustments and fitting. We are considering that NDCI provides a lot of information in terms of chlorophyll weight, so we're planning to use NDCI as our index for comparison, to compare different water bodies around Latin America, instead of creating specific algorithms for specific water bodies. Here's an example of Mirim Lagoon in border of Brazil and Uruguay. We can see some algae blooms occurring here. Next, please. And the idea is to create a Google app, Google Engine app that will provide near real time, we hope so, to upload this information and be able to see over near real time the blooms here, and also plot some graphs to see some tendency of pixels, calculate some algae blooms area, and etc. Next, please. For now, we are thinking of creating a new image collection and upload that to a set. So that's a technical issue we are facing, because the SEAC algorithm, the script, it's very computing demanding, so we can't do that on the fly and online directly. So you need to create an image collection and to upload that into the set. So when you create the app, the user can access this collection. Next, please. Here the different participants' roles. I won't take much time here. So just give. We're doing the courses, right, to get some skills, because in South America here we're still developing our Google Engine and programming skills, so it's been very helpful, this courses, so we're building a team to work on this. Next, please. Yeah. So basically the methodological approach here is to correct the Sentinel-2 collection for atmospheric effects, sampling correction, apply all the masks, and create this new collection. Here we're planning so far to upload that into to a set, a new collection, and with some water quality database provided by different groups or official information, we will validate some algorithms here for chlorophyll estimation and classes of trophic state levels. And with this information, we can create charts, maps, and spatial statistics in terms of occurrence and maximum, minimum, and different stats. Next, please. So here, just an example, what we want the app to look like. So the user would be able to choose location, date, range, the projects he wants to visualize, and charts and some stats, and we'll be able to export all this information into tables and GeoGEE files. Next, please. The study area, you focus a lot on the urban areas. They're facing the algae blooms effects, because the impact of algae blooms are in the reservoirs used for the water supply in the urban. So in São Paulo and Rio and different capitals, Mexico, all around Latin America. So we're looking at these urban areas, so people can actually see what the conditions of the reservoir for the application. And it's very important to highlight that in Latin America we have a very poor monitoring system of in situ data, so the remote sense information will be very helpful. Next, please. I'll give an example in Tietê River in São Paulo. We are using some official data from the Environmental Space Protection Agency. Next. And we're collecting this information to create chlorophyll algorithms. Still not much data. We have so far less than 200 points, but it's still something to build. Although it's not a lot of data, it comprises a very large range from chlorophyll from 0 to more than 500. Next. Next, please. And then the other project we're planning to next is to create this chlorophyll trophic state index ranging from oligotrophic, eutrophic, and hypertrophic. So we can also apply and give this information of different classes. Next. Next. Here an example in Billy, in São Paulo region, the metropolitan region. NVCI shows and highlights very well the algae blooms when we can see. Next. And then with the NVCI, you can derive chlorophyll A or trophic state index, and also the bloom. You can also map if it's a bloom or not. Okay, so that's the basically we are planning. Next. I can just, you can go to the final, because we are facing just I want to bring some issues here in terms of the issues we are facing regarding creating this new collection to upload the assets so people can access the collection straight instead of doing all the atmospheric correction on the fly. And that's one thing. Another thing is how we can manage and share amongst us, the participants here, some in situ data in terms of chlorophyll and etc. So for now, I think that's all. Thank you.
Felipe, thanks, and sorry to rush you, but I really want to get to the panel discussion and take some of these questions further. So I did just want to ask though, because I think it's becoming a recurring theme with respect to water applications. Is the standard Sentinel-2 atmospheric correction insufficient or inappropriate for water applications? Or, yeah, could you shed some light?
For Sentinel-2 specifically, the Sentinel core products for our analysis is not it's overestimating the bloom sometimes, because the red edge band is overestimated in the correction, and also because the fact of Sentinel core, the level 2, is only from 2017 or 18 onwards, and we want to work with the whole collection from 2015. And then we're having issues with using the SIAC because it's very computing demanding. So the alternative is also doesn't quite solve the whole problem.
Yeah, absolutely. And I think there's similar challenges with Joji's project in the Northern Pacific as well, in terms of the I suppose the processing level of data available within Earth Engine. So Noel, I'll give you a heads up. I think we might try and put you on the spot on that topic and Google's thoughts on it towards the end in the panel discussion.
Can I just give a little last comment, Sam, in terms of the continuity of the project, right? I think I'd like to hear from Noel as well, from Google Engine, because, for example, if you create a collection and we need to update that after the project ends, and how other researchers and how Google Engine is looking into that. So we're planning to maybe make it automatic updating, right? So it's just a question for all of you.
It's a good question, and that will be a common one. So thank you. That's definitely something that we at EO Data Science will kind of support you guys to do. It would be terrible to see all the work that's gone into the 32 projects within the program kind of end on a certain date. We'd like to make sure that everything produced within those continues to be available and the outputs can be leveraged. So it's a really good point to make. So thanks, Felipe. Our final presenter is David Fernando Morales Giraldo from the Marine and Coastal Research Institute in Colombia, presenting on coastal erosion and mangrove ecosystems. David, please.
Good morning, everyone, and afternoon or evening, wherever in the world you are. I'm David Morales. I'm a geologist. I'm from the Marine and Coastal Research Institute. This is located in Colombia, and we are adscript to the Ministry of Environment and Sustainable Development. Our Next slide, please. Our project leader is Julian Pizarro. He is a system engineer, and our research group is composed by topographic engineer, geographist, and PhD in oceanography, with our external collaborators that are the Ministry of Environment, the National Natural Park Agency, and some regional corporations for the administration of the environment. Next slide, please. Our main goal is to use the Google engine to develop a digital image processing methodology to assess the incidence of coastal erosion on mangrove ecosystems in Colombia, and besides to strengthen the capacities of the researchers in the use and development of algorithms and applications in Google engine. Next slide, please. Okay, here I'm going to take much more time. This is the main research that we have obtained at the moment. We are working like in two parallel groups. One is the mangroves, the change in mangroves analysis, that is led by the Systems Information Laboratory. These algorithms have been done with using the Sentinel-2, Sentinel-1, and SRTM models to identify where are these mangroves in a specific area. This is the Ciénaga Grande de Santa Marta. It's a vast region that, with an anthropogenic incidence, since the mangroves have a lot of pressure for agriculture and by the seaside with the coastal erosion. These algorithms are thinking to be used in the whole Caribbean region of Colombia to identify this main change in the coverage. Next slide, please. Our next idea is to cross the information that I saw that one of you is also planning to use QuadSat. We previously used some RGs and air to identify the rates of change in coastal erosion. Now we're planning to develop this in the GEO platform. We need to create all the applications and to make all this available for the different researchers that comes to our institutions and for the different corporations that work with us. Also, we plan to cartography the mangrove cover, the change of coastal lines, and implement this in the pilot region of Ciénaga Grande Santa Marta. Besides of that, we plan to identify some coastlines in the change in urban areas or other exposed elements in the coastal region. And this information is planned to be available into portals, into webpages that are part of the National Information System and for the environment, that is from the ministry. And this is going to be in one of the portals is the Sigma portal. I'm going to copy the address on our internet chat. And for coastal erosion, we're planning to do this in Coast Zero. Okay, I think that's all. With the questions, Sam, you can follow with the questions.
Yeah. David, thank you for the overview. I do have quite a few questions. I've worked with mangroves a little in the past. What is your approach that you use for the classification? Could you kind of step us through how you do that? Is it kind of single scene or using a time series of data? Are you using kind of classical machine learning algorithms, or have you taken the deep learning approach?
By the moment, we are using the random forest algorithm, and yeah, we just have identified the information for one data set, but the idea is to use the different times to identify the change on the Siena. This project has been done previously with downloaded images from Spot or Landsat, and that the idea is, well, to improve this and automate this because it has the research institute is in charge to provide the indicators for the Ministry of Environment and improve the management of this area.
Excellent. And your methodology for monitoring mangrove cover, do you think that's something that is kind of more broadly applicable around the world or in other parts of Latin America? Do you think it's kind of scalable to those regions, or would it need optimizing or tuning for local conditions?
I think it's that it's also something that we seek in Colombia, because we have the different coasts, right? We have the Caribbean and we have the Pacific coast. So for us, it's also like a goal to try to make this available not only for the region, but for the other environments that we have inside. So with this in mind, we can say that this could be approachable for the different regions in the world. Let's hope. We hope that we can do that.
Excellent. That's great. Thank you for your presentation. Now I'll invite all of the presenters and Noel and Doug to join us as panelists. Please send as many questions through for those people that are watching this. But no, let's get into the questions. I think there was a bit of a common theme kind of backstage in the backstage chat that I noticed around exchanging of details and exchanging of or potential exchange of ground truth data, of methods, and those sorts of insights. Everybody who is presenting and also who is attending these workshops has the opportunity to put a kind of a one-slide bio in kind of our long compiled list of bios with contact details. So that's a great opportunity for anybody listening to add your details in there, because they will be reviewed later. And if you see someone that's in there that you want to talk to, please reach out to them. It's a great opportunity to shortcut the work that you're doing by picking up some new knowledge or exchanging field validation data to improve your work. So please do that. Now, to the questions. I think there's been a common theme around, as I mentioned before, around the processing levels of some common data sets, MODIS, Sentinel-2, that are available in Earth Engine. Of course, these are very, very big image collections. So we can't do everything within Earth Engine in terms of expecting all of those collections to be there. But Noel, if there does seem to be themes developing around a particular potential image collection or data source, what are the channels to, I suppose, work with Google to say, please consider our data source for the public data catalog?
You send us an email that says basically that. There's a criteria list that it has to meet, but our data guys are constantly ingesting data sets. And some of those data sets actually come from users, generating them in Earth Engine or to load them into Earth Engine. So we've got a process for it. You just send an email to earthengine@google.com with your details, and we'll send you back the criteria list and stuff like that.
Yep. Excellent. That's great. Just out of curiosity, what's the size of the public data catalog at the moment? Have we hit 40 terabyte or petabytes?
It's really close to 40. It's on the order of 38, but that was a few days or weeks ago when I checked. So it's growing very fast. We're basically doubling every year. So it's hard to keep up exactly how big it is right now, but it's somewhere around 30 petabytes.
Excellent. Okay, so onto the more serious questions, and I'll throw this open to anybody who wants to answer it. So there's a lot of Earth observation satellites kind of planned for launch over the next few years, like you know, a lot. Are any of those really applicable to water quality research or water research in general? Are there any of them that you guys are excited about the data that might be available next year or the year after? No?
I guess I'm not interested. I'm not sure which particular missions you're referring to. Whether it's the base mission. I mean, I'm familiar with the ones here going on in the U.S. that are planned, such as PACE or the SBG satellite. But for this particular project, again, because it's fairly short term, we're focused on what we have available, obviously.
Yeah.
Of course. And I did want to touch on, just related to the previous comments about you know, some of the data needs and some of the reprocessing and atmospheric correction, which I didn't touch on in my talk, but is a huge issue, and our team has spent a lot of time on this, and I think it's probably going to receive as much attention as the algorithm itself. You know, there was this international study, this kind of intercomparison of atmospheric correction for water that is just finishing up, and there's some publications coming out, and a few of the members of that team are on our algorithm team. And the survey that I mentioned that was going out to the algorithm group does have some questions focused on the atmospheric correction. So as Felipe mentioned, I mean, it's a huge issue. The other thing kind of related to this, analysis-ready data is becoming a big thing, and it's a big issue, and I think you're going to see more and more of it. And I think if we would have something like that, if Google Earth Engine would have analysis-ready data for water, the confidence in some of this information, and you know, that it's been vetted and it's the best science that went into it, and it would save a lot of lifting from other end users or groups that want to process imagery, if it's been cleaned up and, you know, somewhat certified as you know, ready to go, the surface reflectance data. Sorry, I got a little off task there.
You hit the two main problems that we have with these data sets at the same time, which is quite novel. The fact is that we generally try to bring in pre-built data sets. We don't want to build a data set because the likelihood is high that we'll get it wrong. The reason we haven't reprocessed Sentinel-2 surface reflectance is that the tool that ESA uses to do that processing is open source, but the recipe that they go through is not. They have not made that publicly available. So there are so many knobs on that tool to set and tune that we don't want to do it and get it almost right or slightly different than the one they're producing. So we want to bring in certified data sets that someone else has produced. And to our knowledge, no one has produced certified water quality data sets. Even the Landsat science team has this problem where most of the Landsat science team is quite happy with the surface reflectance calibration, except the water quality people. The atmospheric correction over water is different, or not as good. And there is not a set of Landsat data or even a process for producing the well-calibrated data, or at least not one that is certified well enough that we could just bulk load a bunch of it. So with that said, if there is a consortium or a group of water quality experts that can put their stamp of approval on a particular process and say, this is the one we like and we're not going to change it every week, then it's certainly plausible to be able to run that and produce that. If we're just producing images over water, that of course is a much smaller data set than the whole archive of S2 or Landsat. So it is not implausible for our data team to be able to run that if there's one that everybody agrees is the right answer, or at least the best answer that can be had.
Okay, thanks. That's good to hear. I think, well, as you know, the Landsat team, they've put out this provisional surface reflectance product for water, and it's been good. You know, Nima Pavlon, who's on our team, is on that team, and has so he knows more of the intricacies of it. But AquaWatch has worked with CIAS on this ARD and coming up with what's called product family specifications. So that field is evolving, but I mean, you're absolutely right. We're not quite there yet. But it is a question of who does the processing. You know, if do we do this every time? You know, hopefully we get to the point where there is a certified approach, and so not everybody has to do this or go through these hurdles.
I 100% agree, but I bet the ones of you that are doing your own atmospheric correction are not doing the same atmospheric correction even amongst the teams here. So, like I said, when we can get something certified, we're a lot more happy to go that route.
Okay, thank you. So I did want to ask a question of each panelist here. So, I mean, each one of your projects is very much focused on having an impact. There's a lot of science to be done. There's a lot of processing to be done, but we're all kind of focused on having an impact. So Felipe's work, for example, in Latin America, I can't remember the number off the top of my head, but I think it's around 20 million people in Latin America rely on inland waters for the water they drink. So, of course, improving the quality of those waters is hugely beneficial. And likewise, all of your projects, there's an impact that we're aiming at through this project and the work that follows on. So I want to ask the question of each of you, what is the main barrier that you see you need to overcome, your project needs to overcome to have that impact? I think maybe Dimos, if I start with you with that question.
Sure, Sam, thank you. Yeah, I think the main barrier is efficient communication with policymakers working on the coastal environment front in order to communicate our data-driven products. And these policymakers would be working on a coastal-related climate change mitigation agenda. And this would this would create the bridge with national governments in order to use our mapping products and better inform countries, but also international governmental organizations to enforce and empower the national determined contribution, but also multilateral environmental agreements like Sustainable Development Goals. So I would say we should ramp up the effective communication and build effective bridges to create a large impact for the environment, but also for societies.
Yes, thank you. And Joji, I'd love to hear your comments from the Northern Pacific perspective on what challenges do you need to overcome to have the impact that your project wants to have?
Yeah, I think we are working on the UNEP project, and so that is I think that is very helpful for communicating with the scientists to the policymakers, and of course it is I think not easy, but I think it is kind of one big channel, well, biggest channel for us, I think. Yeah, I think it is really need to how can I say, to find a good or attractive product for them. I mean, for the policymakers, it is a very important issue, I think. Yeah.
Excellent. And David, from the Colombian perspective, what challenges do you face in really delivering on the outcomes that you want to for mangroves?
well, I think that this area has a lot of interest for policymakers and for the community in general. The problem with these mangroves comes from the 60s, 70s, and the past century. So maybe one of the main barriers is the budget for continue our project, because this initiative has to be associated or with economical support, right? So we can maintain and make this sustainable over time. We can afford it maybe with the investment of the Ministry of Environment, as I told you before, since this is one indicator that in this strategic ecosystem for the country. And so in a national aspect, we can, I may say that this is really important for many persons here. And by the side of coastal erosion, is a little bit difficult, this budget, because it's more on the states area, and this could be compromises. But the budget for the next year in the environmental research is going to be compromised besides of the emergency by COVID-19. So we hope that this project could continue, and we could have the researchers and the tools, the systems to can use the Google Earth Engine applications.
Yeah, excellent. Great point. Felipe, I'd love to hear your perspective as well.
Thank you, Sam. Now I'd like to ask a question to Noel in terms of alternatively. Okay, we don't have a full collection of atmospheric corrected for water application, but alternatively, supposedly our projects can generate an image collection. For example, if I can provide an image collection of NBCI for Latin America, can I upload that as a official assets? Or of course we need to talk about that, but or I can keep them in my or the project assets or my personal account for people to access this. I don't know if the other leaders are, how they gonna approach that, how they gonna share the product if it's a collect. That's I'm curious to hear how things work on Google Engine in terms of that. Thank you.
Yeah.
Well, like I said before, the collections that are generated by users are candidates for inclusion in the data catalog, but there's a certain amount of criteria about refresh rate and how many people will use it, that sort of stuff. So we certainly can discuss including those collections. You just have to send us an email with details, and we'll discuss it with you.
Yep, excellent. I think it raises and I'm conscious of time here, I think it raises a kind of a related question at the end of this project in 18 months' time. We all kind of have a requirement to, ensure that the outputs are open access and remain available for the, for the next amount of research and products to be built on top of them. So I think that's, definitely a consideration for us in our support role here, but also for Google and GEO in terms of how we make that those outputs accessible at the end of the project as well. I'm becoming very conscious of the time. I'd happily talk for an amount longer, but I won't take everybody's time up anymore. So thank you on behalf of everybody listening for your contribution to this virtual meetup. We hope it's been of value to you. We hope it's been of value for people that are tuning in now or later. So the recording of this meetup will be made public on YouTube soon. So look out for a link in your inbox for all project participants, and also on social media to find the YouTube listing. So please share that with your colleagues. I think we've realised through this conversation that we've got a lot in common, and there's a lot that we can contribute to each other's projects. So the further we spread that message, hopefully the more benefit that comes back to all of the projects. And finally, I just want to thank all of the attendees who are watching at the moment or tune in later, and remind you that there are 2 more virtual meetups that you are welcome to join in as with us as well. So there's one in 23 hours time, and we'll discuss land degradation, and then agriculture and poverty alleviation the following day. So we hope you can all join us then. Goodbye.